Okay, so we will take a small detour because this is a very important result. We would look at one of the essential properties of a circulant matrix. Actually, for any circulant matrix of this form of circulant matrices, and we are going to define circulant matrix, or the structure that we are going to define is the following. The structure that we are going to define is the first column is arbitrary. If you can choose the circulant matrix with this first column is any values that you can think of, okay, and the subsequent columns are circularly shifted. Okay, so basically the last term in that column will show up at the top, circularly shifted. Okay. So clearly there should be one more family of circulant matrices where you do shifting of the rows. So we are looking at the shifting of the columns because that is the matrix that we have to work with. Okay. The claim is for this family of circulant matrices that your the matrix is, of course, there is this matrix will be toplets. Okay. This type of circulant matrix is always diagonalizable, Okay. So, always diagonalizable with actually a well defined structure. Okay. So, if I take a matrix, so let me just construct a matrix, not necessarily our matrix. So, any arbitrary one A naught A1 through A m minus 1, next column will be A m minus 1, A naught A m minus 2, and the last one will be A naught at the bottom, A1 A2 A m minus 1 as the entry. So, this is the general form of a circulant matrix. The claim is that this matrix, if this is denoted as A is always diagonalizable, and the structure of the diagonalized form is W Hermitian lambda times W, where W is the DFT matrix that we are familiar with a slight modification that it is the normalized DFT matrix 1 over root m W k m. Okay. Normally the DFT matrix has got a 1 over m factor in the IDFT. So, you take 1 over root m with the forward transform, 1 over root m with the inverse transform, it exactly you get the same thing. Okay. So, where W is equal to e power minus j 2 pi over m, exactly the DFT matrix, but with this extra 1 over scale. So, this is a scale factor, normalizing scale factor, and so this is referred to as a normalized DFT. Okay, normalized DFT again, but for the scale factor it is exactly what we normalized DFT. The advantage of this is that W inverse is actually equal to W Hermitian. So, that is the reason why we look at this. Okay. So, what we have said is this matrix A is equal to W inverse times lambda times W. Post multiply both sides by W inverse, we get, by the way, and lambda is a diagonal matrix. We will just tell in a minute what the entries of the diagonal matrix are. Okay. So, if you post multiply, then what you find is that A times W inverse is equal to W inverse times lambda, okay, and the lambda is equal to a diagonal matrix which is lambda naught lambda 1 to lambda m minus 1, where these coefficients lambda m are nothing but the DFT of the first column of the circulant matrix. So, this is k equal to 0 to m minus 1 A subscript k W m k m. So, basically, so it is very tightly coupled to the whole DFT DFT properties, take the DFT of the first column and then you actually use the DFT matrix to, as part of the diagonal structure. So, this is what this result is showing. Okay. So, let us just zoom in and look at this result. So, if I can write W inverse as a in terms of its columns, let me call them as W0, W1, these are the columns of W inverse matrix, Wm minus 1. If you now visualize it in terms of the column vectors, this is nothing but the eigen equation. So, basically the columns of W inverse are the eigen vectors and the eigenvalues are the DFT coefficients. So, let me just summarize that. For any circulant matrix of the form where you are doing circularly shifting of the columns, any circulant matrix, the result is that the columns of the IDFT matrix, are the eigenvectors, vectors. So, basically the eigenvectors are W0, W1, Wm minus 1, these are the columns, and the eigenvalue corresponding to any given eigenvector, eigenvalue corresponding to any Wk is lambda k, which is the kth DFT coefficient. Okay. So, these are the DFT coefficients, the corresponding DFT coefficients. Okay. Very good. So, the way it benefits us is that we now have C circulant. I can write it as W inverse lambda times W, where lambda k will be equal to summation, sorry, let me write it as lambda m is equal to k equal to 0 to m minus 1 C k W m k. Okay. And the vector that we are doing has got only up to nu minus 1 nu. So, basically the corresponding vector that we are working with is C naught, C1 up to C nu, and then there are zeros effectively, because you are taking an m point DFT. So, how many zeros are there? This corresponds to m minus nu. Okay. So, effectively the structure is very similar to a generic one, but this is what we have as the expression. Okay. Now, C circulant inverse. C circulant inverse is equal to W inverse lambda inverse W. Okay. So, C circulant inverse exists if lambda inverses, basically those diagonal elements are not 0. So, this one exists if lambda m not equal to 0 for no wait, how did I define it in terms of, okay. Actually since we are talking about the C coefficients, maybe we just let's instead of this we will call it as Cm. Let me call this as Cm. So, the diagonal matrix lambda is the DFT coefficients of the channel coefficients C naught, C1, Cm minus 1. These are uppercase C's. So, please, okay, uppercase C's DFT coefficients. If none, so the inverse will exist if none of the channel coefficients C sub m are not equal to 0 for any m. Okay. Now, here is a important interpretation, and I think this is where the coming at it from the DSP side actually adds a lot of value. Now, what are the C coefficients? What are the C coefficients if you think about it? What are they? It is the frequency response of the channel, correct? Frequency response of the channel. So, if I were to think of the channel, this is frequency, and think of some frequency response of the channel, and deliberately I will make it touch 0 to make sure that we get this. So, some channel variation where it touches 0 and something, okay, some channel variation is there. Now, what was the task of the DFT or the multi-carrier modulation is actually to divide this into sub channels. So, basically, so you took this particular value, that was the gain for this sub channel. The next one had a gain here, and the next one had a gain like this. So, these are the sub channels in the multi-carrier scheme. These are the sub channels that we introduced, and so somewhere here is the channel, maybe we just for, let us take it at the 0. Okay, so, there is one sub channel for which the tap is 0, again please draw it so that, okay, and then afterwards these are, okay. So, multi-carrier scheme, we know to do water filling, all of those concepts are there. The key element that is okay, I just want to okay, let me see, okay, this is a little wider just to accommodate the fact that I want a 0. Okay. So, what is the interpretation that I cannot invert the C matrix? So, which means that I cannot get back any information that was transmitted on that sub channel. Just think about it. You transmitted information on some sub channel where the channel gain was actually 0. So, which means there is no way you are able to recover it. Okay. So, the implication of Ci being equal to 0, implication is Ci being equal to 0 implies that the ith sub channel has 0 gain, 0 channel gain, okay, has channel gain equal to 0. So, in water filling what would you have done? If the channel gain is 0, SNR is very bad. So, you would have not transmitted any information. So, actually we did not lose anything if you had actually done water filling. So, I has channel gain equal to 0, which means in the general context, this means that there is no signal at the receiver, So, there is no way we cannot, no way we can recover this information. If you had actually transmitted information on that, so there is this, but that particular symbol cannot be recovered, cannot recover the, if you had transmitted Si of n, it cannot be recovered because the channel gain was 0, there is nothing to from which you can detect this information. But in practice what would you have done? You would actually have not transmitted any information if you recall water filling. So, the one that helps us is water filling. Water filling says that no power would have been allocated to this channel. That means no symbol transmitted on Si of n, no power allocated. Okay. Under this condition, the ith sub channel is a do not care, ith sub channel is a do not care, okay, if you have done it correctly. Okay. Now, in practice what usually happens is that this one is not exactly 0, it is some small number, right, it is some small number. So, if you in practice when you take frequency response, you will never get exactly 0. So, effectively what you will find that in practice Ci is something which is very close to 0, but Ci is actually equal to some small value delta. Okay. So, because there are several reasons for it, one is the presence of noise. So, when you estimate something in the presence of noise, you do not get exact values, you get something very small, the presence of noise. Okay, that is an important element. So, we say that when you do 1 over Ci, okay, 1 over Ci, we say that always take the minimum. Okay, do not let it go below a certain sorry, you should take the minimum or maximum, sorry, no, minimum of, correct, minimum of 1 over epsilon comma 1 over delta. Okay. Now, if delta was very small, it will give you something very large, but you always sort of put a upper limit on that. So, this epsilon is like a threshold, is a threshold value. So, you do not let the 1 over C to go too large. So, this is a way by which we manage. So, this inversion of the circulant matrix is really not a problem. So, effectively what we are saying is that C circulant inverse exists. Okay. It, first of all, if it was something that there was no information there, but you still have to invert it in the process. So, which means that some small number will be there in that diagonal element, we will replace it with epsilon if it goes very small, and therefore, you get this information. Okay. So, now here comes the insights that are coming in. So, effectively what are we computing? We are computing 1 over Ci for I equal to 0 to m minus 1. Okay. And what are these Ci's? If you think about it, Ce of j omega is the frequency response of the channel. This is given by k equal to 0 through nu Ck e power minus j omega k, okay, and C subscript k is nothing but Ce of j omega sampled at omega equal to 2 pi over m times k. Basically, it is a sampling. It's the DFT coefficients are samples of the discrete Fourier transform. So, effectively what are we doing in the process? We are at the receiver multiplying by 1 over Ck is the same as doing 1 over Ce of j omega in some sense, right. At those frequencies you are doing 1 over Ce of j omega. This in communications you would have learnt it as a zero forcing equalizer, Okay. Zero forcing equalizer basically says if the channel is C of Z, the zero forcing equalizer, this is the zero forcing equalizer is 1 over C of Z. The problem with zero forcing is noise enhancement, because if C of Z becomes very small, 1 over C of Z will become large. What happens to the noise? Noise gets boosted up. So, the problem with this is noise enhancement. So, if you do not want noise enhancement, there is a alternative to zero forcing equalizer, which is called no, it's called, it's in the same form of channel inversion. Distant feedback is a completely different family. In this itself, it is called MMSE equalizer. Basically, MMSE will set a threshold and then do the inversion. Okay. So, MMSE equalizer, it does not allow enhancement of noise. So, basically it controls the enhancement, and what we have done here is exactly the same as we are trying to do zero forcing. If it turns out that zero forcing is going to cause a problem, then therefore we can achieve it through. So, in other words, the inversion is equivalent to the MMSE type of solution. Okay. So, the conclusion is that we can solve this equation where r hat of n is equal to C circulant times S of n, and we obtain the answer, the estimate at the receiver S hat of n to be equal to C times C circulant inverse. Basically, that is the MMSE approach. times r hat of n. Okay. So, we have managed to completely solve the second part of the this portion also we have been able to solve. Eliminate IBI, and the solution for the result estimate is that S hat of n is equal to C circulant inverse times S of n, r hat of n, r hat, which is the received vector with the CP portion removed. Okay. Now, you look at this and say, well, did you really solve any, did you make any benefit at all? Both cases you are inverting a matrix, okay, and well, so is there really any advantage to the cyclic prefix? And the answer turns out to be yes, and that is a very key element as to why we even worked with the method. So, here is the part that that we would like to really focus on. But before that, maybe just a summary of all the results that we have had so far. Okay, the summary of results that we have is the following. We take a vector of data S0 of n, Sm minus 1 of n, okay, and then we do a the cyclic prefix insertion CP insertion, which means basically this will become a larger vector. Okay, so this becomes the x vector x0 of n xn minus 1 of n. Okay, that becomes my then I combine it to pass it through a channel. So, this is where the unblocking occurs, the parallel to serial conversion. Okay. So, take this information, basically we have inserted the cyclic prefix, then you pass it through the channel, C of z, then at the other side we remove the cyclic prefix or throw away those portions, CP removal, okay, CP removal, and then the post processing that needs to be done. In our case, there will be that inversion of the pseudo circulant matrix. This is the post processing, and then you come out with the vector S naught hat of n Sm minus 1 hat of n. So, at the receiver we have r of n, and after the cyclic prefix removal it is r hat of n, and then the post processing, and that is what we have. Okay. So, the input output relationship is basically given to us in the form, input output is given to us in this form, that there is a circulant matrix, we call it as C circulant, which takes in m inputs S naught of n to Sm minus 1 of n, output r naught hat of n, r m minus 1 hat of n, and of course, the estimation process basically will do the channel inversion. Okay. So, I hope the overall picture is clear. We have done something very similar to the zero padding, but in this case we have obtained a circulant matrix and shown that this matrix can always be inverted. So, here are some comparisons of the two. We had mentioned that we will compare. So, zero padding versus CP, are there any advantages, disadvantages of each of those? So, in both cases the channel length is the same, C of z. C of z is equal to summation k equal to 0 through nu C subscript k z power minus k, that is the same. the bandwidth expansion in both cases, that is the amount of redundancy that we have introduced, bandwidth expansion, that is another name for redundancy. Both cases we have used the same amount of redundancy. So, the bandwidth expansion ratio, how much did you expand by? It is m plus nu, nu is the divided by m, same as n over m. So, in both cases we added new additional samples, in one cases it was all zeros, in another case it was. So, typically we find that the block length, the data that we are processing is much larger than the channel length. So, therefore, this bandwidth expansion is not a very significant element. So, again there is a bandwidth expansion, but it is nominal compared to that. Now, is there a difference in the transmitted power? So, no change in terms of bandwidth expansion. Transmitted power. Now, transmitting a 0 effectively means you are not transmitting anything. So, transmitted power, there is actually an advantage for the 0 padding, because 0 padding means zeros which is not a 0 information symbol, that means there is nothing to transmit. So, this is not a bit 0. So, there is actually no transmission. So, actually you are saving power whenever there is a 0 to be transmitted, okay, 0 value to be transmitted. On the other hand, the CPs are all non-zero values, okay. So, which means that you will transmit all the time, okay. So, in some sense this is full transmission, okay, like normal transmission. So, the CP actually requires slightly more power, okay, very slightly, because the overheads are there, but so the average transmitted power for the 0 padding will be marginally less than the average transmitted power for the cyclic prefix, power for the CP case, okay. Now, this is an important one, actually the symbol recovery, the what happens at the receiver, obtaining the, so symbol recovery part, symbol recovery step, where you estimate S hat of n. In the case of the 0 padding, it is a pseudo inverse, because it is an overdetermined set of equations, okay. Now, what is it in the case of CP? Basically, in the previous case there are m unknowns and n equations, okay. So, where n is greater than m. So, you do the least squares there. In the pseudo inverse case, we do C circulant inverse. This corresponds to a case where we have m unknowns and m equations, okay. So, in some sense the pseudo inverse is probably a little more robust in terms of noise, okay. Now, what about complexity? What is the complexity of the inverse of the circulant matrix? It is very less, because it is, can you just tell me the final expression? What is it? It is W inverse, that is basically would be implemented in a fast algorithm. These are diagonal matrix. So, I just take the DFT coefficients and take the reciprocal, this will be W again, okay. So, definitely CP has an advantage. So, this one has got lower complexity because of the structure of the matrix. In the case of the Moore-Penrose pseudo inverse, there is no structure that can be exploited. You will also have now in the case of the pseudo inverse, the 0 padding. In the case of 0 padding, the pseudo inverse always exists. Pseudo inverse always exists. In the case of the cyclic prefix, we may have to replace the 0 forcing with the MMSE. So, MMSE / 0 forcing will help us do the inversion. So, there is no problem. Okay. Now, at the end of the day you may say, well, did we do all this work for the sake of just a little bit of gain in this aspect? Actually not. So, here is where the crux of all that we have discussed so far. Oh, sorry, I have already crossed my time. Okay. So, at the climax you have to stop the thing, but we will pick it up from here. Let me just sort of give you the flavor of what is going to happen. Okay. The transmitted signal that actually I want to transmit is not, I won't transmit S of n. What I feed to the system is not going to be S of n, but is going to be W inverse times S of n. Okay. If you now plug into the equation that we now have, you will find what advantages you are going to get, and this is really the climax. I was hoping that it will end with that, but it will have to wait for the next time. Okay, thank you.